Hi everybody, welcome to the University of Nebraska Department of Physics and Astronomy coverage of the Eclipse. We've got 2.5 Eclipse experts ready to talk to you and explain what's going on. My name is Timothy Gay. I'm a professor of physics at the University of Nebraska. I've got two other experts with me who will introduce themselves momentarily. The sky is a bit cloudy, but it looks like the cloudiness is abating a bit. So we hope to have some exciting stuff ready for you on this live feed. Let me introduce my colleagues, Richard Green and Dan Claes, and I'll let them tell you a bit about themselves.
Go ahead, Richard.
Hi there. I'm an astronomer at the University of Arizona, here visiting Nebraska where I grew up and was back for a reunion event. And so I'm delighted to be here near the moment of first contact when the moon is just starting to nick that solar disk, and we're looking forward to a clearing sky and a really exciting event here.
And I'm Dan Claes. I'm the chair of the Department of Physics and Astronomy here at the University of Nebraska. Tim assigned numbers but didn't lay claim to the half of an expert, so I'll claim that.
No.
I'm actually a high energy physicist, and Tim is an atomic physicist. We're atop Memorial Stadium's parking garage, so you see the stadium there, just north of us. And as you swing north, you'll see the skies look pretty clear in that direction. And when you turn south in the area we would like to be looking at the sun, a little less so, but there's patches of blue all over the place. You can tell by our mussed up hair that it's pretty breezy, so anything can happen.
So, one thing that we want to emphasize, and we're going to emphasize it over and over and over again, because it's the most important piece of information we can give you, is that you should not look at the sun unless you have good quality approved solar glasses. I'm sure most of you have worried about that, but sunglasses will not work. Blackened film will not work. You've got to have these special glasses. We actually have some material, maybe the camera can pan over to show it. The material on your glasses should look something like this. It's got a black back and a silver front.
It's a sheet of Mylar.
It's a sheet of Mylar. And it has exactly the right optical density to make looking at the full sun safe. But if you don't have glasses with this kind of material, and Dan's about to show you the set.
So you see
like
the shiny silver on this side, the black on that side.
It's probably cutting down the intensity by over 100,000. So those are not sunglasses. They're
Right.
very serious.
Right.
And until totality, even at the last minute with the crescent, it's really, you have to have the glasses on. So we can't emphasize that enough.
One way you can check if your glasses are the approved Mylar lenses is when you put them on, you shouldn't be able to see anything at all except the sun.
A little orange disc left of the sun.
When I've worn these inside, occasionally if you have a halogen lamp or a heating lamp, you can look through these and you can make out the glowing filament directly. But other than the filament of an intense source of artificial light or the natural light of the sun, you should be seeing nothing at all.
And most of these have special filtering as well to cut out even more of the ultraviolet and the infrared, so that it really protects your eye until the very last minute.
So Richard, could you put those glasses on for us? The point here, folks, is that there are two very, very good reasons to wear these glasses. The first is so you won't go blind looking at the sun. The second is that they make you look really cool, sort of like a drummer in a 1970s punk rock band, maybe Devo, and so you can just impress your friends with how cool you look.
Right. And the sun right now looks very good through these glasses. It's not 100% clear, but at least when you look that way with your glasses on, you do see that disk with some wispy clouds coming and going in front of it. So it's worth watching. Now, can we see the bite of the moon already? That's really hard
That's
to
a good
tell.
question. Let's check.
It's only been 10-15 minutes,
Yeah.
so probably not.
Richard,
Maybe so.
Richard, when was the first bite supposed to take place? When will the moon begin to occlude the sun?
At about 11:30, and I'm convinced that the upper right corner, sort of at 1 o'clock or
Being
so,
eaten away.
is actually starting to.
I want to look cool too.
And besides that, all
So-
science observations need confirmation.
So I put on my glasses before I look at the sun, not while I'm looking at the sun. I'm going to take these glasses off. Put those on. Oh yeah,
And so I contend that at about 1 o'clock there's already a bite.
a little bite.
So let me jump in here. For most people, seeing a total solar eclipse is a once in a lifetime opportunity. But because, as we were just mentioning, it can be dangerous for your eyes, we've got a short little clip for you to view. University of Nebraska physics graduate students Carl Aronson and Andrew Vikortowski describe how to watch an eclipse safely.
I think you're right.
What can you expect to see as you observe an eclipse?
First, a safety tip. Protective eyewear must always be used to look directly at the sun.
One of the first phenomena you will notice is called Bailey's beads. What you're seeing is the light shining through the bumpy surface of the moon's craters.
These beads disappear, leaving a single glowing dot. This shining dot, along with the bright circle around the outside of the moon, resembles a diamond ring. That's why the bright spot has been named a diamond.
When the diamond disappears, the eclipse has reached totality. You'll also know totality has arrived because it will become dark as night. Now, it's safe to look at the sun without glasses.
Here in Haymarket Park, you'll have just about 1 minute and 15 seconds to safely view the eclipse without your glasses.
Make sure to check the duration of totality wherever you'll be watching the eclipse.
After 1 minute, put your glasses back on to avoid damage to your eyes.
Then you can see the entire process we just described happen in reverse.
So we're up here on the roof of the parking garage just west of the Memorial Stadium on the UNL campus. We have a telescope up here that we're going to show you later through which we can observe the eclipse. If you've already noticed using your sunglasses, there is now a bite taken out of the sun, so the eclipse has started.
Not their sunglasses, they're
getting-
solar eclipse
I'm
glasses.
sorry, the solar eclipse glasses, my mistake. We also, here on the top of the parking structure, have some visitors from Iowa. We're going to go over and talk to them. They're sitting here minding their own business, but
This is
I warned
beautiful.
them we'd come over and interview them. Hi, welcome guys. Thanks for coming all the way over from Iowa.
Yeah.
Here, I'm going to give you that
Sure.
microphone. Tell us where you're from.
Okay, so we're from Iowa, Grinnell, Iowa.
Ah,
Yep, right.
excellent. Are you at the? Are you at Grinnell College?
We're right next to it. We're not at Grinnell College, but we live
We're
in
like
a great town.
a mile away from Grinnell College.
Okay, I
little
visited
less
there.
than a mile.
I've visited Grinnell College. It's a great town. So why did you come all the way over to
Is it just
Lincoln?
a
Why
big
didn't you
blue
go down to
spot?
Kansas City to see the eclipse?
Look at it.
Ah, okay.
Right. So, yeah, Kansas City was going to be packed
takes
with
some
people,
mastery
and
to
the traffic was
get
going to
the
be
pull it in.
astronomical. So we moved over here.
Excellent. Well, we're glad you came to Lincoln, and I hope you enjoy your stay. Are you going to stay tonight, or were you here last night? Or
We were here last night and enjoyed
Okay.
the town, enjoyed
Yeah.
some good food, and
Excellent.
great community and
Good.
ice cream.
Well,
Great.
and you guys should consider coming to UNL for your college experience. Although Grinnell's a pretty good place too. So,
Yeah.
okay, all right. Well,
All
we'll
right,
get
thanks.
back to the coverage. Thank you. All right, we may.
Look at RJ
We- we-
Studios.
we-
We're having a video about it.
Okay, we may come back and interview you later. So, the clouds don't seem to be abating much where the sun is, but they seem to be getting a bit thinner around the horizon. Ah, now on the television, you may be able to see an image of the sun, and you can see exactly where it's being sort of bitten away at about 1:30, the 1:30 position on the clock.
So look with your solar eclipse glasses. It's a beautiful image right now. Very clear.
I'm going to look with my solar eclipse glasses.
What's interesting, of course, is that the ancient system of astronomical magnitudes is in steps of roughly a factor of 2, and that's our eye's natural sensitivity threshold. So we're not going to feel like it's getting dark until the moon's light's been cut the sun's light has been cut almost in half by the moon's disk obscuring that part of the sun. So it still seems like a sunny day, and since the clouds are thinning, it's looking brighter and brighter, but
So
we'll get there.
That's something that confuses most people that ask questions. They expect that this morning, we'll get now darker and darker and darker, and it'll be like advancing night already, not realizing that we have pupils that dilate in response. We accommodate to that drop in intensity, and I think so far the drops in intensity that you'd ordinarily see from midday to noon to mid-afternoon are far more intense. It isn't until about, I don't know, more than 95% of the sun's got to be covered before you even notice that anything's going on.
Really twilight, that's right. But the magic of that minute and a half we're going to get is the stars will come out. It will be actual night. So we're looking forward to that.
So the Earth and Sun do a never-ending dance around the solar system, but once in a while the moon cuts in, and University of Nebraska physics graduate students Carl Aronson and Andrew Vikartarski will explain how often this happens.
Pop quiz, Earthlings.
How often do total solar eclipses happen?
About every year and a half, about every 50 years, or about every 200 years?
The correct answer is about every year and a half. But you have to remember that eclipses can take place nearly anywhere on the planet. Any one particular point on the Earth may experience a total solar eclipse only once every few hundred years. In fact, there hasn't been a total solar eclipse anywhere in the continental US in nearly 40 years.
Groovy. So after the 2017 eclipse, how long do we have to wait to see another one in the US?
It turns out we won't have to wait very long. The next US eclipse is only 7 years from now in 2024. But you'll have to leave Nebraska to see that one.
Okay, I call shotgun.
You can't call shotgun 7 years from now.
Can too. I just did.
Our boss, Teresa Paulson, says she loved it. It's looking good. Stand by, guys. All right.
Hi folks, welcome to UNL's coverage of the eclipse. We're standing here on the roof of the parking structure just west of Memorial Stadium, where the Department of Physics and Astronomy has a big telescope. I'm Tim Gay. I'm professor of physics at the university. I'm one half of 2.5 experts that are going to tell you about the eclipse, and I'll let them introduce themselves.
I'm Dan Claes. I'm chair of the Department of Physics and Astronomy, a high-energy physicist in actuality. Immediately behind me is the observatory that Tim referred to. It's a 16-inch reflector Cassegrain, ordinarily used for student nighttime observations, but it's been retooled with the appropriate filter and set to track the sun, and those are the images we keep cutting into.
Hi, I'm Richard Green. I'm actually an extragalactic astronomer from the University of Arizona, and back home to Nebraska where I grew up, and thought this would be a great place to come because Lincoln is just inside that wonderful path of totality. So standing with my colleagues, enjoying talking with you.
One thing we've been emphasizing over the course of the morning is that the sun is incredibly bright, and it's only safe to look at the sun with approved solar glasses, not sunglasses. Don't use sunglasses, use solar glasses that have the proper optical density to cut out the sun's rays. Now, some of you may be asking, why is the sun so bright? It's an amazing astronomical object. Actually, as far as stars go, the sun is an incredibly average star, average size, average power output. And our solar system is probably a pretty average sort of solar system with a very average central star. But one of the interesting things, and there are many interesting things about the sun, is the huge amount of energy that it puts out. Some of you may be aware of Einstein's famous equation, E equals mc squared. That equation says that energy and mass are essentially the same thing. They're interchangeable. There is a constant of proportionality, which is the speed of light, c squared. But we can then get a feeling for how much energy is contained in mass if we consider, for example, the atomic bomb that was dropped on Hiroshima, Japan in 1945. The amount of mass that bomb converted into energy was about the mass of a postage stamp. Now the sun uses the same mechanism, nuclear fusion, to produce the same kind of energy. Actually, the atomic bomb used nuclear fission, the sun uses nuclear fusion, but they both are mechanisms for turning mass into energy. While the bomb used about 1 postage stamp of mass to produce that energy when the bomb exploded, the sun turns about 20 million tons of mass into energy every second. That's why you've got to wear those glasses. That's why in the winter when you hold your hand up, it still gets warm, even though the sun is 93 million miles away. So that's an interesting thing to consider, but make sure you're wearing those glasses is the bottom line. Now we're getting ready for another video that we'd like to show you.
So a total solar eclipse creates this corridor of darkness in the middle of the day. University of Nebraska physics graduate students Carl Aronson and Andrew Vikortowski will throw some shade on the subject in this next video.
Hello, darkness, my old friend. During a total solar eclipse, there is literally a place where the sun doesn't shine.
The Earth is about 3.7 times wider than the Moon. This globe and this ball have roughly the same relative size scale, so we're going to use them to demonstrate how an eclipse happens on Earth.
In a total solar eclipse, the moon moves directly between the sun and the Earth and blocks the light, causing a large shadow on the Earth.
The center of this shadowed area is the darkest and looks like nighttime on Earth. This area of total darkness is called the path of totality.
Totality has been known to confuse wildlife. Birds become silent during totality and then start singing again as the sun redawns.
Good morning, Carl.
Good morning, Andrew.
So we're on the parking garage next to Memorial Stadium, and we mentioned that we've got a 16-inch Cassegrain reflector telescope in the Student Observatory, ordinarily used for students' nighttime observations and studies. But as I mentioned, it's been retooled. It's got the appropriate filter, and it's been set to track the sun.
Call from the local television station 5 years ago. They said, we've got problems with UFOs. There's a UFO buzzing our...
The two undergraduate students that are doing all the real work for us today. You want to introduce yourself?
Hi, I'm Ellie Feiss.
Tell us a little bit about yourself.
So I've been an astronomy TA for the past couple years, so we're really excited to finally be able to use this telescope to look at the sun and monitor the eclipse, so yeah.
And with you today is?
I'm Zach Rohde. I'm a senior physics major here at UNL, and I've been a TA for this astronomy class for about a year now.
Tell us a little bit about the instrument that we're standing right in front of.
So it's a Meade 16-inch LX200. It's really easy. We just have to set it on the sun, and it tracks its way through, so we don't have to keep monitoring it to make sure that it's centered and where we want it to be all the time. It makes it real easy on our end, and real easy for students to be able to do projects up here through the astronomy class and through their classes that they have to.
So you had an open house here last night?
We did. Last night we had.
Did you see any eclipse?
No, there was no eclipse last night. We were looking at Saturn and then Jupiter for a little bit before the clouds moved in front of it. We had probably about 50 people from the public came out to view. We had 2 telescopes set up out here on top of the parking garage where you've seen people sitting out there in the parking. It was good. The SPS Club, the Society of Physics students here in the physics department, were doing demonstrations as well on things like angular momentum, things of that nature. It was really cool.
So not far from here at Haymarket Park, where there's a Salt Dogs Day game, there's also a science fair where a lot of your fellow SPS students are doing the same thing for the public there. So what had to be changed to be able to operate this way in the daytime to get images for the sun?
One of the more important things that we had to do was get a solar lens for our telescope. So before that, we hadn't had ordered one, so we had to order a special one for that. Usually, we will have to align the telescope by hand, but for this, we just kind of used a different alignment system using some of the focusing and viewer scopes on the telescope to concentrate on the sun. So that was about what we had to change for viewing the sun through this.
And maybe you should thank your professors for letting you out of class today so that you can.
Yes, thank you, professors, for letting us be able to do this. So yeah, we're really excited for this opportunity.
All right, thanks. Oh. Earth is the only planet in our solar system that experiences total eclipses. University of Nebraska physics graduate students Carl Aronson and Andrew Witarkowski size up the reasons why.
Even though the sun and the moon appear roughly to be the same size in the sky, the sun is actually much larger than the moon.
Let's see how big they are relative to each other.
Imagine the sun's diameter fits snugly between home plate and second base.
Hey Andrew, how'd you get to second base so fast?
A gentleman physicist never tells.
If the sun were that big, then the Earth would shrink to about the size of this exercise ball.
And the moon would be the size of this Stinger dodgeball. So during a total eclipse, how can something this small completely block out something this big? The answer is perspective. The moon only appears to be the same size as the sun because the moon is a lot closer to the Earth than the sun is, about 400 times closer.
You know how things appear smaller when they're further away? Well, the sun is really, really far away. I'm squishing you!
So maybe we'll interview some more people that have come up to the top of the parking structure. The good news is that I'm starting to see shadows associated with people standing around the parking structure. So that means that the clouds may be dissipating a little bit. I see here one graduate student in physics. Tell us who you are, guys.
The microphone.
My name's Brett Gergley. I'm a second-year student in the physics program here at UNL. We just came up the rooftop because supposedly totality is a little longer here than it was at the Haymarket Park. This is my friend from Michigan. Yep. She drove all the way from Detroit, actually.
Excellent.
Yeah. My name's Jared. I'm friends with Brett. I'm driving down to Scottsdale, Arizona, and I came a few hours out of the way to visit my friend and get the best view possible. So
excellent.
Well worth it, in my opinion.
Do you go to school at the University of Michigan or Wayne State or?
Actually, yeah, I have a graduate degree from Wayne State.
Okay, I just visited Detroit. It's a great town.
Yeah, it's
Are you from the city or are you from a suburb or?
I currently reside in Arizona, but I was in the city and the suburbs back and forth.
Okay, great. Well, thanks for showing up, you guys.
Oh yeah.
Okay,
absolutely.
let's.
Thanks for letting me hang out.
Okay. Let's see where we are.
Go ahead. So if you look at the sun and not directly without the eclipse glasses, you're going to notice something amazing today, and that there's this giant ring that the cloud cover has created that surrounds us. So we've got the sun centered like a bullseye in the center of a big ring. You want to?
And so that's from the ice crystals in the cirrus clouds that are blocking our view a little bit, but the angle on the sky is 23 degrees and the ice is catching the sunshine, making that rainbow ring around it. So it's a beautiful, if unrelated phenomenon all to itself.
Something we wouldn't have noticed if we had had the perfectly clear skies that we were hoping for, but now we get the benefit of, I'm standing in, I can feel the sunshine, I'm casting shadows, and my eclipse glasses are giving me beautiful images of that eclipsed sun, but at the same time we have enough cloud cover that we can pick up that little meteorological effect too, which is pretty cool.
And
I have a question for the astronomer that's been bugging me. How much has there ever been an eclipse event where on day one the moon sort of scraped the bottom of the sun, and then on day two the moon sort of scraped the top of the sun or something? How much does the moon move in angle from day to day?
So to get an eclipse, as we know, there has to be a perfect alignment where the sun, the moon, and the earth all have to be exactly on a line. So the earth's orbit around the sun defines a plane, it defines a flat plane, and the moon's orbit around the earth is tilted at about 5 degrees with respect to that plane.
Yes.
So therefore, sometimes eclipses don't happen at all, and sometimes indeed they can be grazing partial eclipses. And
Yes.
so, and since there are a couple of eclipses per year, there's all varieties and they happen frequently.
Okay.
But you were bringing, oh, you want to cut?
Let's jump to a clip here. For most people, seeing a totally solar eclipse is a once-in-a-lifetime opportunity, but it can be dangerous for your eyes. So watch in the little next segment when University of Nebraska physics graduate students Carl Aronson and Andrew Vygotsky describe how to watch an eclipse safely.
What can you expect to see as you observe an eclipse?
First, a safety tip. Protective eyewear must always be used to look directly at the sun.
One of the first phenomena you will notice is called Bailey's beads. What you're seeing is the light shining through the bumpy surface of the moon's craters.
These beads disappear, leaving a single glowing dot. This shining dot, along with the bright circle around the outside of the moon, resembles a diamond ring. That's why the bright spot has been named a diamond.
When the diamond disappears, the eclipse has reached totality. You'll also know totality has arrived because it will become dark as night. Now, it's safe to look at the sun without glasses.
Here in Haymarket Park, you'll have just about 1 minute and 15 seconds to safely view the eclipse without your glasses.
Make sure to check the duration of totality wherever you'll be watching the eclipse.
After 1 minute, put your glasses back on to avoid damage to your eyes.
Then you can see the entire process we just described happen in reverse.
About why the sun is so bright, and the fact that the sun is actually an engine using nuclear fusion to convert mass into energy. It converts about 20 million tons of mass per second into energy. That's a phenomenal amount of mass, and it's why the sun is so bright. But there's some interesting details about how that nuclear energy gets into the light we see from the sun. Richard, tell us about that.
It doesn't get straight out, so the nuclear fusion machine is only in the inner quarter of the radius of the sun, and above that is a zone of very dense gas that tends to absorb those gamma rays and X-rays that are generated in the fusion process and sends them scattering off in a different direction. So they aren't streaming out of the sun, they're leaking out of the sun, bouncing around like a rubber ball before, and it takes about 1 million years from the time the energy is first generated until it gets to the staging point where it can actually get out of the sun. But even that isn't enough because that radiative layer is still well into the interior. There's a little transition zone that's very thin where a lot of action happens, and from then on, from the last 25% of the last quarter of the radius, it's like a boiling pot that bubbles of hot gas float up from that boundary to the surface and break at the surface and release the energy there. So the whole process of, from the time that the fusion liberates some of Einstein's mass energy to the time that it streams to us to warm us on a cool day takes 1 million years plus, and then these massive bubbles that on the actual surface that are carrying the energy from below and bursting on the surface to release.
So it's a little bit like the dorm room I used to live in. You turn on the heat and get some vague amount of warmth 7 hours later or something.
It's very much like that.
Okay.
And so if that furnace ever turns off, it'll take us 1 million years to know.
Okay.
Since we've got everybody's attention looking at the sun, let's point out again that we've got this thin cirrus cloud layer that's obscuring it slightly, but it's producing a secondary beautiful effect. You can see this rainbow ring that surrounds it. If you put your eclipse glasses on and look at the sun, we've just been talking about how powerful it is, how enormous in reality it is. It is 109 times wider than the Earth, but it's 400 times further away than the moon. And it means that the size, the angular size of the sun is actually quite small. And looking at it safely during a sunset, or now with your eclipse glasses, you can convince yourself that if you look at the sun, you can blot it out with a thumb held at arm's length, or in fact, your pinky finger. The nail of your pinky finger is big enough, twice again as big as it needs to be, to block out the sun. Sun is actually covering a very small portion of the sky, but the fraction of its energy that we receive, described by Tim, is what makes it feel so warm, despite that apparent size. I remember my grandfather, who I don't think graduated high school, when he learned that I was a physics major, he had asked me, did they ever figure out how something as small as the sun can produce enough energy for life on Earth? And I was aghast and my jaw dropped, and I was flustered in trying to explain to him that the sun was actually bigger than the Earth. And then I was a little embarrassed because he clearly was, and retracted the question right away.
But it's a good question because, that number, the sun is burning up 20 million tons of itself every second. So how long can it possibly last? And the answer is about as long as it's already lived, about 5 billion years. The Earth is 4.6 billion years old. The sun's a bit older than that, but about 5 billion, and the sun will continue to burn hydrogen, which is what it's doing now, for another 5 billion years. It will then, and Richard can explain this better than I can, it will then convert itself to burning helium, and then it'll go crazy. But Richard can tell us that story.
That's a complicated story, but it's all like water running downhill. The energy wants to leak out at a very particular rate. So when physics changes the rate that the generator is working inside, the star has to adjust itself to change the slope so that the energy leaks out at the right rate. That's called becoming a red giant star.
Yes.
The outer boundary of the star expands enormously. It gets very much cooler. So the surface temperature of our sun's about 10,000 Fahrenheit.
Right.
And a red giant star is half that at best. And so that star, our sun, 5 billion years hence, will be out to the orbit of Mars or a little beyond. So it undergoes a major change. So we have 5 billion years to figure out how to move to a better vacation spot.
Earth is closer than Mars, so Earth will be in the interior of the sun's surface.
In 5 billion years, but not before.
And this, of course, is a very important reason that we should all be supporting science funding, because we're going to have NASA figure out a way for us to all get off this rock and move into the next solar system, because in 5 billion years, there won't be any more left of this Earth.
So shy of that time scale, since we were talking about variations in the solar system, people often ask, isn't it a spectacular accident that the moon appears to be the same angular size as our sun and provide this perfect total eclipse? In reality, the orbit of our moon has changed over time. In earlier eons, the moon has been closer to the Earth and was too big to make the eclipses quite as spectacular as what we're hoping to see today. And in a few tens of millions of years hence, it will, due to tidal forces, gradually drift out into a larger orbit and cover much less of the surface of the sun. We're lucky to be in 2017 to be able to witness the eclipse the way we will.
Absolutely.
There's another interesting thing about the Earth-Moon system. It's easy for us to think about the Earth sitting here and the moon orbiting the Earth, and that's true. The moon is about 286,000 miles away from the Earth on average. But in fact, the Earth and the moon are more strongly coupled than that. In other words, they both orbit around the Earth-Moon center of mass. The moon technically doesn't move around the center of the Earth. It turns out that the Earth-Moon center of mass is about 300 miles away from the center of the Earth. So the moon orbits around that point 300 miles from the center of the Earth, but the Earth does too. It's wobbling with a radius of about 300 miles about this point, which is the center of mass of the Earth-Moon system. So it's a complicated orbital system. And of course, when you throw in the sun and the effects of the other planets, all heck breaks loose.
It's also true, didn't the Earth lock up the moon? Doesn't the same side of the moon face the Earth all the time?
That's right.
So that the moon's revolution is the same as its orbital rotation. So that was the excitement about sending probes to orbit around and see that backside that we otherwise never see from here.
Right.
So.
Well, the moon is weird for many reasons. It's anomalously large compared to the host planet, the Earth. There are a few other moons in the solar system that are as big as our moon, but they're associated with the big gas planets, Saturn and Jupiter. And Titan, I guess, is associated with Neptune, isn't it? Or Uranus, I can't remember. This is the one-half expert coming in. But it's very strange for a rocky planet like ours. There are 4 rocky planets: Mercury, Venus, Earth, and Mars. And it's very odd that one of the rocky planets, namely our planet, has this big, huge moon orbiting it.
Time to cut in for another important message. Total solar eclipse creates this corridor of darkness in the middle of the day. University of Nebraska physics graduate students Carl Aronson and Andrew Vikartowski will throw some shade on the subject in this next video.
Pop quiz, Earthlings.
How often do total solar eclipses happen?
About every year and a half, about every 50 years, or about every 200 years?
The correct answer is about every year and a half. But you have to remember that eclipses can take place nearly anywhere on the planet. Any one particular point on the Earth may experience a total solar eclipse only once every few hundred years. In fact, there hasn't been a total solar eclipse anywhere in the continental US in nearly 40 years.
Groovy. So after the 2017 eclipse, how long do we have to wait to see another one in the US?
It turns out we won't have to wait very long. The next US eclipse is only 7 years from now in 2024. But you'll have to leave Nebraska to see that one.
Okay, I call shotgun.
You can't call shotgun 7 years from now.
Can too. I just did.
We've been wandering around the rooftop of the parking structure, talking to visitors. We have a special visitor today, Tony Saros of the Physics and Astronomy Department here at UNL. He was chair of the department for many years. He's a theoretical atomic physicist. Professor Saros, why did you come up to see the eclipse?
Well, this eclipse is a big event in my family. My son is writing an article. He's been commissioned to write an article about it. And he's going to Carbondale, Illinois, from Chicago, with my daughter, Ann. And they're both in Carbondale at the moment, and that has 2.5 minutes of total eclipse. Here we have 1 minute 24 seconds, I believe, but I am taking this opportunity for this once-in-a-lifetime event to see what it's like. And,
so one of the important things here is that Tony's a pretty cool-looking guy just on his own, but when he puts on those sunglasses, he looks even cooler. So this is one of the ancillary benefits of wearing these. Not only will you not go blind if you wear these glasses, but you'll look really cool.
Well, that's just one of the side effects of being a scientist.
Right. I like the way you think. Okay, we'll go back now. Do we have another video queued up, or?
No, you can look at the sun.
You can look at the sun. Thanks.
It's about what percent?
Excited about for an eclipse like this is to study the low intensity outer atmosphere of the sun that normally can't be seen. And so
most people are unaware that, like, the Earth has an atmosphere, the sun has an atmosphere all its own.
It's not really exactly clearing up,
and
is
so
it?
First, the temperature drops just above the surface of the sun, but that's the place where all that energy is being deposited, and so the temperature turns around and goes up to over 1 million degrees. And so that part is what, both of those parts are visible when the moon's disk just blocks the very bright surface of the sun that we now see, the photosphere. So the layer just above that is called the chromosphere, because when you take a picture of it, it's bright red. It's a thin little ring right around the sun, and that beautiful red color comes almost entirely from hydrogen atoms that are 3 to 2. It's the hydrogen alpha line in the deep red, and so people who take color photos who are lucky will see flashes of red through the moon's canyons. And the moon is a beautiful occulter because it's not a disk. It's got mountains.
Craggy.
It is, and so it has mountains and craters, and when there's a notch, you look much closer to the sun's surface and can see this transition layer in the atmosphere where the temperature is dropping and then rising again and glowing bright red. Then above that is what we're really looking forward to as it turns completely clear in another half hour or so, and we see the faint corona, and that's this crown, this extended atmosphere where the plasma, the gas that's had electrons knocked off its atoms, is over 1 million degrees. So there's so much energy has been injected into this thin, tenuous gas that it's glowing through 3 different mechanisms. It has atoms that are making sharp energy transitions, spectral lines. It has a continuous white light from electrons orbiting around magnetic field lines and producing radiation that way. And then the dust in the plane of our own Milky Way comes right into the sun, and so that dust is so warm that it also scatters sunlight and glows all on its own. So this extended, beautiful, wispy outer atmosphere, the corona, is never seen from the ground except when the sun is completely blocked by a solar eclipse.
So this is one of ground observation few opportunities to study it, right?
It really is.
will you still be able to see the
Corona.
The corona?
Yeah.
And so we'd have to be lucky. It stands out against the question was, if it's cloudy, can we see the faint details of the outer surface of the sun? The answer is, of course, it depends on how thick the cloud is, but they are rather faint. And so the thicker the cloud, the less of it we'll actually get to see. And so we got to keep our fingers crossed that this gets thinner and clears out some. So that
even if the clouds pass and they open up so that we have an opportunity to see that, we should mention that those less intense light are actually safe to observe without the solar glasses, but you dare not take off the eclipse glasses until you can no longer see the sun at all. When you no longer can see anything, including the sun, it's because the disk of the surface of the sun has been occluded completely, and then it's safe for about a minute and a half to take those glasses off, and then you will be able to see what won't go through these lenses here, the glow of that corona.
But the stars will come out and it will be like a wispy, faint cloud around the sun.
So are we going to have to take off the glasses to see the total eclipse?
You'll see more
What was the question?
when it's really total. He says, should we take off our glasses to enjoy the total part of the eclipse?
Only during totality.
Yeah.
So if you are watching the sun and the sun vanishes completely, it's because the moon is in the way.
Yeah.
It's blocking you from the direct light of its surface, which is the dangerous light to view. And you can prop those glasses up for a little while to watch or look for, hopefully, and see that corona that dances around that ring of fire about the dark disk that's the moon in its way. But you got to be prepared to drop those glasses back down before the sun comes back up.
Are you folks from Grinnell, Iowa too? Okay, so you all drove out.
Came together, yeah.
Are either of you, are you an astronomer or what's
No.
your, are you a science teacher? What's your?
I did teach high school science, but I don't any longer. I stay home with my kids.
Okay.
Done web development as well.
And with soon to be our dog.
Okay.
And you are interested in growing up and being an astronomer? Physicist?
I used to be actually interested in being an astronomer, but not anymore.
What do you want to be now?
Kind of.
What do you want to be now?
A computer scientist.
Okay, well that's a good one too.
Okay, we need those.
That's really great.
That's a good one too.
And the scientists who use the computers to make models have made a prediction for what the corona is going to look like today. So when it gets really dark and it's cleared out, what they think for today is that they're going to be little thin streamers coming vertically off the pole of the sun.
Cool.
The sun spins around, and the sun has a cycle, and so it's magnetic energy that drives everything we see on the surface. And there's not much action right now because the sun is within a year and a half or so of the very minimum of the cycle. So that means that it's going to be kind of a modest corona today, but they expect vertical streamers coming out of the poles, and then they expect some action around the sun's equator, so that there should be what they call helmet streamers.
Wait, so is this live streaming right now?
You're on, man.
So I have a question for Richard, actually. It's been bothering me. So Richard, could you talk to us a little bit about sunspots? Are sunspots like islands of magma or something on the surface, or what are those spots? Why are they so black?
It's a great question. And so you remember the group They Might Be Giants sang a song about the sun, right? The sun is a miasma of incandescent plasma. So the sun's surface is very hot gas. And any features that there are on that surface are produced by magnets, by magnetic field. So deeper in the sun, between the place right below where the pot starts boiling, this magnetic field is generated, and it's transported to the surface in those bubbles we talked about. A sunspot is a place where there's a whole lot of magnetic pressure, magnetic power, and so the bubbles can't come up. And therefore, even though the gas is very hot, it's a couple hundred degrees cooler than its surroundings, and it looks dark to us. So magnetic pressure is actually preventing the boiling pot from bubbling right there as much.
So if we could see the dark sunspot by itself, not surrounded by the rest of the sun, it would actually be bright as well.
It's still very bright. It's just not quite as bright, so it looks dark in contrast.
But now another thing that you pointed out puzzled me, because you said that the surface of the sun, which is the coolest part of the sun, is about 10,000 degrees Fahrenheit.
Yes.
That sounds pretty hot. How can magnets even exist? I mean, wouldn't the iron melt? I mean,
absolutely. So it's not a permanent magnet like an iron magnet.
Okay.
It's I'll do a dance. So there is because it's so hot, some of the electrons are knocked off their atoms.
Okay.
And so electrons moving around are an electric current by definition.
Yes.
And when you have an electric current, you make magnetic fields. And
yes,
so,
just like a solenoid.
Exactly. So this plasma, this gas with some electrons knocked out free, can create currents which create magnetic fields, and those fields are transported in the conductive gas bubbles.
So it's actually the gaseous plasma that's producing, the charged plasma that's producing the magnetic field.
Yes.
Wow.
Yes.
Okay.
It's a real dynamo. There's some kind of slipping between layers of rotation of the sun, and that slipping works just like a generator, a dynamo generator on Earth, to create big currents which create big magnetic fields. Then they get tangled, then they break, and when they break, they release enormous amounts of energy, and that can be a solar flare.
Okay, great. I think we're going to go into the telescope now with Dan to explore what's going on.
Cool.
Okay. You're probably tired of listening to
exactly
the professor's
look
gap.
at this. Bah.
Students are looking after everything in our Student Observatory, and I want to introduce them again. Introduce yourself. Tell us a little bit about yourself.
My name is Zach Rohde. I'm a senior physics major here at UNL, and I'm a TA for the Astronomy 103 class, so I get to deal with this apparatus and help the students do projects.
My name is Ellie Feist, and I'm also a TA for this class. I'm a senior advertising and public relations major.
Talk a little bit about student projects that are done in this facility.
So we have a variety of projects that we do throughout the school year. One of them is observing double stars. Another is looking at star clusters. We also look at Jupiter, Saturn, the moon, among other things.
And how often will a student in an astronomy class have an opportunity to come look through this telescope?
So if they're in the class, we are open 5 days a week here, and they can come out any of those nights and come and do a project or just extra credit or just come and view for fun if they're interested. We do have at times when students come out when it's cloudy and we have to unfortunately turn them away then. But every clear night we have a great view here.
You said every 5 nights a week?
5 nights a week.
So.
Excuse me, 4 nights a week. I'm sorry, I misspoke.
I'm still impressed.
4 nights a week. Yep.
And then we schedule several times during the school year a public night, like you had last night.
Yep. We have a public night when just anyone from the public can come out and view whatever we're able to see that night with the weather conditions and such. Such as last night we had a public night and we viewed Jupiter until it got cloudy and we were unable to see it. And then Saturn, we had a really good clear view of that. We were able to see the rings and it was a great night for it. The SPS Club, the Society of Physics students, also was out here doing presentations, demonstrations for the public, so they can practical applications. You can really feel with your hands physically the science behind these phenomenon.
So Ellie, tell us a little bit about the modifications that needed to be made to turn this from a nighttime observing facility into something we could use for the eclipse.
Yeah, so the modifications, the first thing we needed to do was get a solar cap, because we normally use this at night, and if the sun shines through the telescope, then it pretty much ruins everything. So we had to get the solar cap for that, and most of the adjustments after that came with how we would align the scope. Usually we use a polar alignment where we'll find 2 different stars in the sky, and from there it actually can have a sense of where it is. So for this, we just use a different alignment system where we use some of the finder scopes on it, and we through the finder scopes, we centered it as close as we could to the sun, and then with the shadow or the focus from the light on the ground, then we aligned from there, and then the rest was just done manually through the lens. So yeah.
Okay, thanks Ellie, thanks Zach.
Thank you.
So the Earth is the only planet in our solar system that experiences total solar eclipses. University of Nebraska physics graduate students Carl Aronson and Andrew Vikartowski will size up the reasons why in our next video.
Hello, darkness, my old friend. During a total solar eclipse, there is literally a place where the sun doesn't shine.
The Earth is about 3.7 times wider than the Moon. This globe and this ball have roughly the same relative size scale, so we're going to use them to demonstrate how an eclipse happens on Earth.
In a total solar eclipse, the moon moves directly between the sun and the Earth and blocks the light, causing a large shadow on the Earth.
The center of this shadowed area is the darkest and looks like nighttime on Earth. This area of total darkness is called the path of totality.
Totality has been known to confuse wildlife. Birds become silent during totality and then start singing again as the sun redawns.
Good morning, Carl.
Good morning, Andrew.
Okay, so we're back. Indeed, the sun is being occulted, but not only by the moon here at the moment. So we are hoping against hope that the thick cloud goes on its way and we get to see totality in a half hour in its full splendor, but there's time.
Yeah, there's still patches of blue all around us, and sunlight sneaks through every once in a while. So
we're very hopeful. So. And we're hoping, for instance, we can see those shadow bands right before the moment of full eclipse. That little sliver of sunlight that's left undergoes the same process that makes the stars twinkle in the sky. There are, at certain layers, there are bubbles of air that are a little bit warmer than their surroundings.
There's little eddy currents in the air.
And they act like little prisms to throw the light back and forth. And so that crescent gets projected back and forth and flits across just as the shadow is advancing, and makes light and dark bands that we hope we can see.
Yeah, those are hard to capture. Most people have anecdotal records and little else about them, but there is certainty, and if they'll last 30 seconds or something, right? I mean, there's a little bit of time to view that.
Yes.
You'd have to tear your eyes away from the sky and look down at the ground. They'll look something like, you know, when you look in a bright sunny day at the bottom of a swimming pool, and the refraction of the light that the water produces has these little lines that wiggle on the ground. It'll be something similar to that. So we were talking to an aspiring future
So we're going to talk to
scientist.
some other people over here. Where are you guys from?
We're from Omaha.
Okay, here,
We
you
go to
should
school here.
hold that, yeah.
Hello. What station is this?
This is not a station.
Oh.
This is the UNL Department of Physics and Astronomy. So
Awesome.
you're all from Omaha?
Yeah, we all went to high school together too.
You can hand the. So are you going to UNL now, or are you okay? Are you?
I can't quite tell where
So
it
you
is.
guys look like you're about freshmen. Are you guys freshmen? Okay. So you, what? Have you ever seen an eclipse before?
No.
Okay. It seems to be getting cloudier and cloudier.
I know. We were gonna ask you, is it supposed to clear up?
We don't know. We
Sorry.
don't know. Tell me what are you majoring in at UNL?
Well, I just started graduate school for speech language pathology.
Okay, excellent. Okay, so you're not a freshman then. That's what you're telling
That's
me.
correct.
Now,
I'm
what
not a
about your
freshman.
friends? What are you guys majoring in?
I'm a fifth-year senior in electrical engineering.
Excellent. Okay.
Fifth-year senior studying water science.
Water science.
Yeah.
That's going to be big. So
We'll
what do you
see.
want to do when you graduate?
I want to work for like an engineering consulting firm for like
Okay.
water resources.
In Nebraska or?
We'll see. We'll see.
Seems like it's big in Kansas, Colorado,
Yeah.
and Wyoming too.
Yeah, big in the Midwest for sure.
Yeah. Okay, good. Now, do you have a now to give it back to your friend there? Do you have a job lined up after you graduate?
Well, I've been working at an engineering consulting firm for the past 2 summers, so I have a job lined up there if I want, but I'm down to explore other places too.
Yeah, good. Have you had a good time here at UNL?
I did. I actually had you as my professor for Physics 211.
Excellent. Okay, yeah, they come and yes. I occasionally remember names.
I wouldn't expect you to. There was like 200 people in the class.
No, it was those are hard to remember all those names. Good. Well, thanks for coming to visit. Any other thoughts on the eclipse?
I hope it gets.
I hope the clouds go away. Yeah, that's good. That's good. All right, let's move it back to the expert. Yeah, sorry.
Okay, we're back on. I actually learned something new for this eclipse because the ancients always wanted to be, once they figured out what they were, wanted to be able to predict the next one. But the exact next one, the one closest to this one, has to have 4 things come out right again. And so it turns out that means the moon, the earth, and the sun have to line up the way they were, but there are 4 different ways of measuring a month. That is to say, when does the moon end up exactly where it was? So one way has the moon in its same physical place in its orbit relative to the fixed stars, which is nothing we can observe.
So made one full circle.
We just calculate it. What we call a lunar month is, when the moon is at the same phase as it was a month ago. But because the Earth is going around the sun and the moon is going around the Earth, our lunar month is 29.5 days. That's the long one, and all the others are about 27 days. There's the time that the moon crosses the sun-Earth orbit at exactly the same place, and that's about a 27-day month. And then there's the time, the one last one, is where the moon makes its closest approach to the Earth again, and that's also 27 days and a fraction. And so every 18 years, all those periods line up roughly with the same number of passes of the moon, and then we get an eclipse almost like this one. So that cycle is called a Saros Cycle from the ancient Greeks, and there's a series of cycles depending on whether the moon is the eclipses are coming from the south and going north, or north to south, and when they started. And so in any given decade or so, we're in the middle of 40 Saros cycles, give or take. But this one has a number and has eclipses that all look very similar.
So that doesn't mean the band of totality will fall in exactly the same spot on Earth, though.
That's right, because even though there are whole number in advance in 18 years, they aren't perfect. They aren't perfectly aligned, and so in fact the next one will be about a third of the way around the Earth to have the same path. So it won't be as nice here. But on the other hand, there are many other such cycles going, so there will be another good eclipse in a few years that goes across North America.
So the mathematical gymnastics you were describing to find that cycle was first applied, I think, by Thales, the ancient Greek philosopher, in about 610 BC. He used that based on the record of the immediately previous eclipse to predict when the next one would come. And he got the year right, but
not the month.
Not the month, no.
And finally Ptolemy was the one who really got all the math down close enough to have a workable system. Here's a guy.
What's like the worst thing that could happen if you looked? So how long is the eclipse going to be? The total eclipse?
1.5 minutes.
Okay,
roughly.
So, yeah, kind of have to be like watching out for it. Is it going to be like? So what's it going to look like?
So what will you see during that 1.5 minutes?
Yeah.
Richard, you were explaining that before.
The stars will be out.
Yeah.
It will be twilight, but not like just after the sun sets. It'll be twilight glow on all the horizons if it were clear. Now what the clouds will do is another story.
Look, north looks good. We should be able to see twilight.
We'll see a twilight.
Okay, so we'll see that over there.
We'll see a twilight glow, and right around the sun you might see little red dots from the lower atmosphere above the sun peeking through the moon's valleys.
Oh, whoa.
And outside the sun, there'll be these streamers of super hot gas that'll glow sort of faintly white or maybe green if you
And so
really have
the worst that could happen is we don't see that stuff. We don't see
Right,
the...
it'll go all the way dark, but it'll be so cloudy we don't see stars and we don't see the beautiful streamers around the sun if it's really thick
Are
cloud.
you guys pretty sure that the clouds aren't gonna thin?
Are you gonna give us a guarantee?
Wait. I think it's going to clear.
We are always hopeful.
Okay.
That's,
but I promise you, there's no way you're going to miss totality.
It will
Because
get dark.
you can tell the difference between right now and midnight, right?
Yeah.
Okay, so that part you'll experience for
Okay.
sure.
So we'll all see the sky go dark in the middle of the day.
Okay.
But what we hope is that those clouds back off a little bit so we see the beautiful part right around the sun.
Do you have a coin
Yeah.
on you? I need a coin.
What do you think? What do you think's going to happen?
Well, I hope
okay.
they clear out. I'm not sure, but
Okay,
I don't know,
wait,
it's-
you see blue there? You see
Yeah.
blue there?
Yeah,
you
yeah.
see blue there?
We're all hoping that blue comes over us just
and
at
we
the
have
right
like
time.
20 minutes for that blue to reach there.
Yeah.
Okay.
So start blowing hard up there.
I think that we should actually do our best to answer the young man's question. And
Okay.
You seem to be engaging in a patently unscientific method, but I brought in a much more scientific method. Heads, the clouds will go away. Tails, they won't.
And it's... Who asked you?
That looks
2 out of 3?
like- that looks like you can't tell heads or tails on these newfangled coins. It's
Anyway,
tails,
right?
so it looks like it's going to be cloudy the whole
But we
way.
gotta do best 2 out of 3. That's the only way.
Okay,
See,
we'll try it again. Here we go.
Oh, well.
You buy us that experiment.
Yeah.
You have another
Tails.
coin?
Yeah. Yeah. I'll go search for another
Best 2 out of
coin.
3 coins.
They gave us the wrong answer, Tony.
Thanks.
Come back with your next question.
And
It's
we're
okay.
gonna keep hoping.
So for most people viewing
It looks
a total
like the
solar
blue's getting
eclipse,
bigger.
See?
it is.
It is.
Well, actually,
Yeah.
Thank you.
So keep up the good work. For most people, viewing a total solar eclipse is a once-in-a-lifetime opportunity, but it can be dangerous for your eyes. University of Nebraska physics graduate students Carl Aronson and Andrew Vikartowski describe how to watch an eclipse safely in our next video.
What can you expect to see as you observe an eclipse?
First, a safety tip. Protective
If that
eyewear must always be used to look directly at the sun.
One of the first phenomena you will notice is called Bailey's beads. What you're seeing is the light shining through the bumpy surface of the moon's craters.
These beads disappear, leaving a single glowing dot. This shining dot, along with the bright circle around the outside of the moon, resembles a diamond ring. That's why the bright spot has been named a diamond.
When the diamond disappears, the eclipse has reached totality. You'll also know totality has arrived because it will become dark as night. Now, it's safe to look at the sun without glasses.
Here in Haymarket Park, you'll have just about 1 minute and 15 seconds to safely view the eclipse without your glasses.
Make sure to check the duration of totality wherever you'll be watching the eclipse.
After 1 minute, put your glasses back on to avoid damage to your eyes.
Then you can see the entire process we just described happen in reverse.
that solar eclipses have played a really major role in the development of the GPS. You say, wait a minute, what? What does that mean? Well, it turns out that the GPS is crucially dependent on the principles of Einstein's second big theory of relativity, the theory of general relativity.
The theory of gravity.
The theory of gravity. And the theory of gravity was one of the first important pieces of experimental evidence was provided by the astronomers. Richard.
So the theory, which was visionary for its time and now, says that matter bends space, so that a photon, a light ray traveling along, defines what a straight line is, but if it passes near mass that makes gravity, its path will be curved, it will be bent, and it almost acts like a lens. And so this was so controversial and so unexpected that Einstein persuaded his German colleagues, an astronomer, to go out to a total eclipse and take a picture of the stars right around the sun to see what they looked like at the moment of the total eclipse when the whole sky is dark. And sure enough, because the sun was making the straight line flight of the starlight bend a little bit, then the angle made the stars look like they were pushed outward from the sun, and the magnitude, how far they were at that field of stars was actually distorted, was exactly what Einstein predicted. And so it was a stunning experimental observational verification and validation of his theory, and his theory of general relativity stands in that form today.
And it was that announcement of that discovery that made Einstein a household name. I mean, that's what made him famous, was the vindication of general relativity.
So if you watched Nat Geo, they went into all the drama of the personalities involved, but in fact, this is a classic, beautiful case of a physical theory prediction that then people went out, made an observation, and validated it, and the theory was correct.
And that emphasizes another crucial thing about how science, and physics in particular, works. When you have a theory, like the one that Einstein developed to explain gravity, you have to test it experimentally. And you test it, and of course there are the first tests, which are then very exciting if they agree with what the prediction of the theory states, but you keep testing ever more accurately to ever better precision. And if a theory or a physical idea can uphold every experimental test, can pass every experimental test, then you begin to really believe that it's true. And this is so important that the only way, the only physics laws we have are the ones that have basically passed every experimental test we can throw at them.
If you're talking about physics theories, calculations, we were talking a little bit earlier about the first successful prediction of a solar eclipse. The Babylonians were able to predict lunar eclipses, but that's kind of an easier task.
The Earth's shadow is much bigger, for one thing.
And they had a lot more data, because we've all known numerous instances where we were told we could go out that night and watch for a lunar eclipse, because the lunar eclipse is seen by the entire hemisphere on Earth. But something,
oh, look at that.
Yeah, if you look at the image that we're projecting now,
it's nice
that's beautiful.
Nice to have a telescope to show us that the sun, and the remaining bit of the sun, is turning into just a crescent at this point.
You can sort of see it now.
So it's clearing just a little.
It's just clearing a little bit.
Yeah. So it's coming out enough from the cloud cover.
Yes.
That I can see it with.
So we can notice indeed that it's significantly darker now. It's starting to dim into twilight with that last 10% sliver on there. So we'll have to start watching out for Bailey's beads and the diamond ring and all the phenomena that those great videos have been telling us.
We're about 10 minutes from totality.
Yes.
And it is getting
noticeably
darker.
Yes. So a disadvantage of having clouds is that they do scatter light.
Yes.
So they blur the edges of what we're seeing and make that crescent sun a little softer than we'd like it to be, because there's so much information that we could get from looking at how the moon's craters and valleys shape.
I don't know, Richard. It's looking pretty nice now. You should take a look.
Yeah, you should.
I think that
even with that cloud, we can see right through it.
We can.
But it's remarkable how I can look at that with my open eyes briefly.
But it's not a good idea.
But it's not a good idea.
Yet.
But it's remarkable that we're getting that much light out of just a little sliver. And it's still quite bright. I mean, it's very bright.
Yeah, I would have thought it would be darker than this.
But you can actually see it. You can really see it now.
Looks like looks like I think tails was supposed to be that they were.
Okay.
Aha, it could be. So
The theory of coin tosses
yes,
gets thrown in the trash bin of history.
Oh, we would love that minute and a half of totality to be as good and as thin cloud as we're now getting.
We're about 8 minutes away.
So
8 minutes away, and it's
103?
102 and 36 seconds. So, I mean, you look out around, it's not nighttime, right?
Not yet. Which tells you how much of that how much light still comes off of even that tiny
just that
sliver.
Well, it's that natural log effect you were talking
The
about.
image we're transmitting now, that is gorgeous.
Yes. So
look at that.
Yeah.
That's
We're
pretty darn
hoping to
cool.
see the full effect very soon. So these are interesting eclipses, the ones in the different part of the solar cycle when the magnetic field is particularly active and creating many, many sunspots. That same magnetic activity also spews a lot of material out into the corona and energizes it. And so those solar eclipses have much bigger, brighter streamers. Higher magnification?
Yeah, they switched to the other telescope, the big telescope.
Okay. So now we're really seeing the limb.
We can watch for beads, Bailey's beads on this image,
Absolutely.
right?
I mean, we
Now,
may see them by eye if it's really good.
Explain to the one-half expert, what are Bailey's beads? I don't know about those.
So the sun is spherical.
Yes.
And the moon is kind of spherical. It's craggy. It has mountains, it has craters, it has fissures. So you try to block, even if they're approximately the same angular size, you try to block a sphere with the craggy sphere. There will be little notches where light can leak through around the edges.
Sure.
At the moment that we're approaching now, as we approach totality, when we get down to just the point where there will only be those little cracks of light, those will make the little, what will appear to us as little dancing
So it's not
beads.
a diffraction effect, it's just it's an occlusion of mountains effect.
Yes.
Yeah, that's right.
Got it.
It's
Although
transmission through a pattern.
One interesting question is, the moon is spherical with bumps on it due to mountains. The sun is spherical, but the sun is more technically prolate, oblate, because of the centrifugal force felt at the equator, and because it's a gaseous object, it tends to be a little flattened.
So
how big is that effect?
It's fortunate for us on this eclipse.
Yes.
It's smaller than the difference in the moon's distance. So the moon's shadow on this one is particularly large, and so it will get both the equator and the poles.
Okay.
And so in this case, that fraction of a percent is not going to be a big impact for us.
But I remember that the sun's diameter is about 866,000 miles or something like that. I think that's right. Just a bit less than a million.
Its diameter is about 2,000 miles.
The sun.
The sun
The sun is
the moon. Oh, sorry, I'm so sorry.
Something like that.
And 400 times bigger than the moon.
So
how
many miles how many miles less is the pole to pole distance of the sun than the equator diameter, right? Something.
It's a fraction of a percent.
Okay,
So-
fraction of a percent. Okay.
So
it's quite.
It's a small
It's quite small. Yeah.
That's right. So
Whoa.
we're looking up, and it's that
Whoa.
crescent is slimming rapidly here.
Excellent. And you can really now see it.
And we're seeing these factors of 2 rolling as the sky gets darker and darker, and it's feeling more like night.
It's like early evening.
That's right.
Yes.
But there's like almost no sun left.
I'd say mid-evening now. It's actually almost more impressive than the crescent itself is the darkening. I mean,
that's right.
That's very
it is
impressive.
really quite amazing. And at the very last moment will be the diamond ring when there's only one canyon left.
Yeah, one canyon left.
And we're gonna one last flash, and then we'll be in true darkness.
And Richard, how many minutes of totality will we have?
We have about 1.5 minutes here.
Okay.
Because we're right at the edge of the moon's umbra of its full shadow.
Yes.
And they'll get close to 2 minutes further south.
Okay.
But we will get a spectacular time. Clouds notwithstanding.
Now, you may think that since it's getting so dark, it's okay to look with your eyes, but do not do it. It's still very, very bright, and you may blind yourself if you stare directly at the sun. So don't do it. Use your solar glasses.
So totality is coming on
Yeah,
us.
we've got 3 minutes or so.
Yeah.
As one of my colleagues used to say, there are many good reasons not to wear laser goggles until you go blind.
Yes. And so keeping those glasses on until that crescent disappears is our strong advice here. But we're starting to see some of the...
It's getting rather dark.
Yes, and some of the automatically triggered, the street lights are coming on now as the photocells respond to things darkening.
I meant to talk to the city about that.
So it's still a very thin crescent. And what the people with the scientists with clear views are going to be very eager to see the shape of the coronal streamers today and what the distant magnetic field of the sun is actually doing. You knew, by the way, that there's a citizen science project going on where there is a set of identical telescopes being set up by high school and college students across the whole path. And so they're going to get a 90-minute, more or less, map of the inner corona, and that's never been done before in history. So the solar physicists are going to learn how the magnetic field coils up, how it generates activity at the base of the corona. And you would say, darn plan, you would say, gee, aren't there space satellites that do that? And the answer is yes, but they don't point perfectly, and so the disks they use to block out the sun and study the corona all the time don't go nearly as close to the sun as the moon's disk, which is the perfect match. So this will be a unique, and it will be all generated by students and by citizens.
It's cool.
A unique data set for studying the sun's corona. Boy, it's going fast.
Wow.
We got about another minute and a half.
Yeah,
it's
still,
now it's getting dark.
Now the lights are starting to come on here. The photocells have started to activate the parking lot lights where we're standing.
Now it is nighttime.
And we just see that very, very, very thin crescent remaining.
The birds have not yet figured out that something is amiss, but they will soon. Oh, and you can see the twilight all around us.
Twilight is on all the horizons now. So it's what you'll never see at a sunset, because one horizon's dark and one's light.
Right.
Here they're all the same.
Right.
And so the clouds low in the north which is where the video image is pointing, shows you. And that very last crescent is fading away behind our cloud cover here.
Yeah, you can now,
And
yes.
And
yeah.
There it is.
Oh my gosh.
And so,
wow.
It is extraordinary. There's a beautiful view of the chromosphere, and we can even see some of the coronal streamers if we stare at it for a while, because it is faint. And so it is truly dark like late twilight.
Wow.
But
It's
we
remarkable.
are indeed
You can hear people cheering from the ballpark.
Yep.
It's remarkable.
That is extraordinary.
It is safe to look
It's
now.
safe
It
to
is
look
safe
now for
Take
about
your glasses
10 more
off
seconds.
and stare as hard as you can.
Now look as hard as you can because it's about to stop.
Yeah. And so part of that chromosphere really does look a little bit red to me.
Yeah.
You know, at sort of 11 o'clock, it looks pinker.
Yeah, it's odd. I have not heard any birds roosting. My memory. There it comes.
There's the
Yeah.
Thank goodness it's
And
coming
so
back.
We're getting the reverse diamond ring.
Okay, we'll have to put
Back
glasses
now.
back on.
And
Is the sun coming back out?
yeah,
you're
sure
right.
is. That's
Sure
the
is.
huge diamond ring. So
Stop. You got to use your glasses now, guys.
That was it.
Use your glasses.
Oh, that was so cool.
I thought the birds would be roosting.
Let's hear it for nature.
One of my memories of the 1964 total eclipse in Maine was that it was very cloudy like this, but the birds were roosting.
Yeah.
We were in the middle of a forest almost.
Right. And you know, it may be that the 2-minute one version is more.
They
we're
may
right at
start
the
to
edge,
roost.
Yep.
so it
Yes,
just moves across.
Sure.
But still,
We're going to talk to our friends from Iowa again. What do you guys think?
That was the
You're the most
thing.
vocal Iowan we have here. What did you think?
That was so cool. Wait, if you squint, you can only see a sliver of it.
Don't look at it. No, don't look at it now. Yeah, there we go. Put those glasses back on, guys.
That was so
What do you
cool.
think, sir?
That was pretty amazing.
Yeah.
Now the ring that's lit up, and even the cloud coverage still kind of shows.
Yeah, it really was even impressive through the cloud cover, I thought. So,
Oh yeah. A lot of power up there.
Right.
yeah.
Right.
Look how fast it's.
Professor,
brightening.
let's go over and talk to Professor Staris. Professor Staris, what did you think of the eclipse?
Well, it was impressive. I'm sorry we couldn't see the stars, but
that would have been cool.
we've seen totality.
Yeah, we've seen totality. We have reached totality.
Wow.
Let's go talk to my friends over here.
Worth the trip?
Oh, absolutely. I mean, you know, clearer would have been even better, but even
We have
so, it's just a
we have some
spectacle.
UNL students
Absolutely
who
is.
are enjoying the total eclipse, drinking their favorite beverage. So, what did you guys think of the eclipse?
That was nuts. That was so
Good?
cool. I'm glad we could see it with the clouds still.
Yeah. No, that was great.
The clouds kind of made it cooler because of the sunset all around.
Other opinions, pass it around.
Yeah, it felt like we were on another planet for a second there. It was pretty cool. I liked it. What'd you think, Connor?
Did you see the birds flying around?
Birds were everywhere.
That was crazy.
That surprised me. I thought they'd be roosting. I thought because my memory of the eclipse, I saw a total in 1964 before you guys were born, and it was totally cloudy like this. We drove from Ohio for 1,000 miles to see this eclipse, and it was cloudy. But the birds, I just remember it was black as night, and the birds were roosting because they were confused.
Anyone else? Any opinions?
Got an opinion for it?
We all thought it was pretty amazing.
Yeah.
It was cool.
Enough said there.
Yeah, cool. Thanks, guys.
Thank you.
Haymarket Park, where they took a timeout.
Oh yeah.
They stopped the game.
Oh yeah. No, the birds are waking up again here.
So let me film our day
Yeah, the birds are going nuts. Huh? Ah. What do you think? We've come to interview you. Did you get some good shots?
I believe I got some pretty interesting ones.
Yeah, those look good. Yeah.
From just prior. And then
Now, were you using a special filter on your camera, or?
yes, this is actually one that I purchased just at the
Oh,
store.
okay.
It's
That's like
simple
our
disposable
sunglasses,
one.
basically.
Yeah,
our
pretty
solar
much.
solar glasses.
Mhm.
Yeah.
And then I bought some solar glasses there.
Okay. Excellent.
Then when the actual eclipse happened, yes, I'm a shutterbug.
Yes. That's why we're interviewing you. You look like you knew what you were doing. So, there. Yeah.
And then as it eclipsed, all 4 directions.
Ah, yeah, that was remarkable. Just how it looked.
And then with the clouds refracting the sunlight, some of the colors in these images around the halo.
Yeah.
I really enjoy.
Remarkable. Yeah, that was the thing that really surprised me, was how cool. I mean, you could see the coronal ring, even though it was quite cloudy. I mean, it was it was
so bright.
Yeah, it was so cloudy that you couldn't see it through the glasses, but you could see it.
No, you couldn't.
Yeah. So, and you picked that up on your camera. Good. Thank you.
You're welcome.
Any thoughts, guys? What do you think? What did you think?
Oh, it was beautiful.
Okay.
I thought it was beautiful.
Okay.
It was perfect.
It was definitely very beautiful. I was expecting something good, and it was something great.
Yeah.
Just really happy that the clouds cleared out in time.
A little bit.
Enough
Yeah.
for us to see.
Just at the last second, it was perfect timing, really.
Yeah,
Right.
it's also kind of nice with the cannons going off and
Yeah.
people just shouting in awe, you know.
Yeah.
So that was kind of nice to kind of have this experience in my lifetime, and you know, it was beautiful. It's almost perfect. So.
Are you a student at UNL?
Yes, I am. I'm a fisheries and wildlife major.
Excellent. Good.
Yeah.
Okay.
So
Yeah.
Kind of nice coming out here.
Huh. Thanks, guys. So let's now get the impressions of our team. Dan, what did you think of the eclipse?
So despite the cloud cover, the ring
We have
came
a physics
out.
major. Get over here.
The ring came out spectacularly. So
Yeah.
that was remarkable, and that opportunity to see a hollowed out sun, that was pretty cool.
It was a great opportunity as a student with
The events that the physics department and the SPS club has put on here for me to get every opportunity and to view it and all the science behind it, and it was great all around.
Yeah. Physics in action.
Physics in action.
Let's interview our other student here. Yes. Tell us your name and your major.
My name is Ellie Feist, and I'm an advertising and public relations major.
And you've been helping with the telescope.
Yes, I have. I've been an astronomy TA for the past 2 years, so this is my 3rd year working.
Excellent.
So we're very excited to see the sun or the eclipse. So.
She's a Renaissance woman. She does advertising and astronomy.
Yeah.
It's what our field needs.
Yeah.
Yeah.
Yeah. Yeah, you should go into science publicity.
I've actually thought about that,
Yeah,
so that's a possible career
Yeah,
path.
that's a
but
good career.
Never know.
That's really great.
Okay, and let's get Richard's take on this too.
I convinced myself that I could actually see the chromosphere on the upper part of the eclipse, and so seeing that bright red right around the surface of the sun was really a thrill. It was a little disappointing that the clouds were as thick as they were, but the beautiful ring, and I could convince myself I could see a little bit of corona, and this is my first total eclipse after in all these years, and I was thrilled. And so grateful for the hospitality.
Thank you for coming and helping
Yeah,
us out.
You saved us by showing up, so we appreciate you being here. Yeah, I mean it was remarkable in the sense that it gives you a sense of the vastness of the universe, and you realize though that these astronomical bodies, which you're used to studying in textbooks, actually can have an effect on your actual experience of the Earth. So that was really cool.
And as people who teach physical science, we can't have a more thrilling moment than to have millions of people looking up at the sky and getting interested in what's going on. I mean, that's as good as it gets for us. And
Asking questions.
Right. What's happening?
Everybody is naturally curious about the universe they live in, And of course, that's what science is all about, answering those curiosity-driven questions. One of the reasons I love my job as a scientist, as a physicist so much is I spend my days answering questions that I've come up with out of curiosity. And it's a good way to go.
Well said.
It's moments like these that really make me glad I'm a physics major and in the science field at all. It makes you fall in love with science again, with events like this where it's just, you're just awestruck sitting here staring up into the sky.
And that doesn't go away.
And he'll be receiving his stipend for that ad soon.
So thank you for joining us. We're atop the Memorial Stadium parking garage here on the University of Nebraska campus, and you've been watching the total solar eclipse with Professor Tim Gay, Professor Richard Green, graduate student Zach Rohde, Ellie behind me, and I'm Dan Claes. Thank you for joining us.
Thanks for joining us, everybody.
you.